Hello, this movie is for independence and dependence. If you're in your guided notes, I think it's around page 12. You have completed formative 4, and now we're looking at how to determine if data is independent or dependent. At the beginning of this unit, we were looking at different concepts, and we were thinking, oh, well, those two events, those are definitely independent. Those are definitely dependent. And then there were some that we needed more data. For example, if I were to pick a student from the freshman class and pick a student from the senior class, those two events definitely and obviously independent. Because picking someone from the freshman class will have no impact on who I pick in the senior class. Two totally different events. Another example, picking a student who's in singers and picking a person who is, or a student who likes to sing, that probably is dependent. I bet the one has a direct relationship with the other event. So sometimes things are obviously independent and obviously dependent, but sometimes they're not so obvious. And so what we're going to be looking at now is, what do we do when the events are not as obvious? How can we test for independence? And that's what we're going to do here. If events A and B are said to be independent, then what we know is this. Conceptually, we know that, now remember, this symbol means given that. The probability of event A given that we're looking at B is equal to the probability of A. Since it doesn't matter that B happened or not, it will be equal to the probability of A. Let me give you an example here. Let's go. If we look at this example, skateboards, snowmobiles. Not sure if there is a relationship here, but if I'm looking at the probability of someone liking to skateboard given that they like to snowmobile, that would be equal to the probability of skateboard if these events are independent, because it didn't matter if they like to snowmobile or not. Now, the same would be true the opposite direction. If we're looking at the probability if someone likes to snowmobile, given that they like to skateboard, if that's equal to the probability of snowmobile, then the events were independent because it didn't matter if they liked to skateboard or not. So, testing for independence, we can use this, the given that. So probability of B given A, if that's equal to the probability of B, it doesn't matter that A happened or not. We're just going to get probability of B because events are independent. Now, mathematically, we know independent events, the intersection, we multiply the two probabilities if they're independent. So the probability of A given B is the probability of A and B over the probability of B. That's the definition of conditionals. Probability of A and B, if independent, is A times B. The B's cancel, and we get probability of A. So if events are independent, then we get probability of A. So probability of A given B is the same as probability of A if events are independent. There's two tests for independence. One is using the definition, and that is what we just talked about. A given B is equal to A, B given A is equal to B. And two is using their products. At the very beginning of this unit, we learned if events independent, then the and you multiply. And what we're saying here is if the and is equal to the multiplication of these two, then events were independent. We're going and doing its converse. So let's take some data from the class. Maybe we don't have data because you're watching a movie, you were absent. So I'm making up data here. Let's put this in. 4, 2, 6, 2, 8, 10, 6, 10, 16. Complete the two-way table, done. What is the probability that a random student selected in our class has dark hair and light eyes. Dark hair and light eyes would be dark hair and light eyes is 2 out of the 16 total, which is 1/8, which as a decimal is 0.125. And so that's the probability, dark hair and light eyes. What is the probability that a random selected student has light eyes or light hair? Light eyes, or, I should do the symbol, or light hair. That's going to be light eyes is 10 out of 16, which is right here, light eyes. Light hair is right here, 10 out of 16. But what's happened is we've included these 8 people twice. So we have to subtract off the overlap of 8 out of 16. Now this is going to give us 12 out of 16, which is 3/4, which is 0.75. So this reminds us of and or. Now let's look here. Are the events of having dark hair and having dark eyes independent? So what we can do is use 2 definitions. We're going to look at the first definition, and I'm going to your completed handbook. The first one is using if A given B is equal to the probability of A. So we're analyzing, is the probability of dark hair given dark eyes if that's the same as the probability of dark hair, then we know it didn't matter that they had dark eyes because they're going to have dark hair regardless. So let's test this out. Probability of dark hair given dark eyes is going to be dark hair given dark eyes, 4 out of 6. So let's go over here. This is 4 out of 6, which is 0.6 repeating. I'm going to round, take it to the thousandths, and then I'm seeing if that's equal to the probability of dark hair. Now, dark hair is 6 out of 16. So I'm going to say 6 out of 16. And 6 divided by 16, take it to the thousandths, is 0.375. Now, these 2 decimals are not equal. And because they're not equal, we call these dependent events. So the one is depending on the other. So therefore, these events are not independent because their decimals are not equal when you're doing this definition. Now, one question might be, could I have done light eyes and light hair? And the answer is yes. You would also get dependent events if you did it that way. Now, there is a second definition, which is using their products. And so we're going down here, we're going to use products. So second definition, if the product of A and B, I'm going to be more specific. The product of dark hair and dark eyes is equal to the probability of dark hair times the probability of dark eyes, then we know the events are independent. So dark hair and dark eyes is 4 out of 16. So we put 4 out of 16. And we see if that's equal to probability of dark hair is 6 out of 16 times probability of dark eyes, 6 out of 16. So 4 out of 16 we know to be 0.25. And over here I'm multiplying these fractions to get a decimal, and I'm going to round to the thousandths, and I get 0.1406. So I'm going to make that 0.141. And these are not equal. Therefore, events are independent or dependent. So you will get using either of the two definitions here for independence, you will get that having dark hair and dark eyes are definitely dependent events. You are more likely to have dark eyes if you have dark hair. That's what this is saying. So the events are not independent. And that's how you test for independence when things are iffy. So I'm going to go down here. We've got another set of classroom data. And I'm going to just give you some data. 11, 2, 13, 1, 1, 2, 12, 3, and 15. Complete the two-way table. There's your data. Find the probability of not pants. This is called the complement of having pants, which is not pants, and that would be shorts. So that's 13 out of 15, which is approximately 0.866, which would be 867. What is the probability of a person in the class wearing both short sleeves and shorts? So the probability of short sleeves and shorts is equal to, let's see, short sleeves and shorts is 11 out of 15. So we do, which is about 733.733. What is the probability of a person in this class either wearing pants or short sleeves? And so pants is 2 out of 15. Short sleeves is 12 out of 15. But there's an overlap of one person. And so that gives us 0.867. Okay. Are the events of wearing shorts and wearing short sleeves independent? If you think about that one, I have a theory. I would think that they would be dependent because it seems like if I'm wearing short sleeves, then I'm probably going to be wearing shorts. Not always, but what we could do is run the stats and see if the events of the class data would make it independent or dependent. So let's use the two definitions. The first one is I'm going to say the probability of wearing shorts given that I've got short sleeves. If that's equal to the probability of shorts, well then these events are independent because the one did not matter. It was not hindering or affecting the other one at all. So the probability of shorts given short sleeves, let's look at that, would be 11 out of 12. So we've got 11 out of 12 here, which when you get the decimal is 0.9166, so 7. And then the probability of shorts would be, shorts 13 out of 15. So 13 out of 15, oops, wrote it in the wrong spot. 13 out of 15 is 0.867. And these are not equal. Now they're a little closer than the other events, and sometimes close is okay, but these guys, they're not too close. So we would say that the events are dependent. And then the second method we use is using products. So if the product of shorts and short sleeves is equal to the product of shorts times the product of short sleeves, then we know we have independent events. That's number 2 down here, using products. So we have shorts and short sleeves, which would be 11 out of 15. Is that equal to probability of shorts? 13 out of 15 times probability Probability of short sleeves, 12 out of 15. So 11 out of 15 is 0.733 equal to, this gives me about 0.693. And these are not equal. So these are dependent events. And that's how you test for independence or dependence, actually. You do these two tests. You could use the definition. You can use the products. Now we have more class data. I'd like you to take Formative 5. And then this is a great, absolutely great example to review some content and to test for independence. Thanks for watching this movie.